Hey there and welcome. Today, we're going to tackle a really cool calculus problem. How in the world do you measure the length of a curve that doesn't go in a straight line, but instead kind of spins around a central point? Let's dive right in.
So think about this for a second. Imagine you're trying to trace the edge of a perfect spiral galaxy or map out a planet's orbit. You can't just lay down a ruler, right? So how do you actually calculate the length of a path that's defined by its angle and its distance from a single point? Well, that's exactly the puzzle we're going to solve today.
Now, you might be thinking we need some brand new, super complicated theorem for this, but believe it or not, the secret is actually hiding in one of the very first formulas you ever learned in geometry. We're about to see how the good old Pythagorean theorem is the hidden engine behind the whole formula for polar arc length.
Okay, so to wrap your head around this, just picture taking one single teeny tiny step along any polar curve. That one little step is actually made of two even simpler moves. First, there's a radial change, which we call dr. That's just you moving straight out, away from the center. And second, you've got a tangential change, rd theta, which is like a tiny sideways shuffle you do as the curve swings around.
And here's where it all clicks. It's beautiful, really. Those two little movements, the dr and the rd theta, they perfectly form the two legs of a tiny right triangle. And the actual step you took along the curve, that's the hypotenuse, ds. So thanks to Pythagoras, we know that ds squared equals dr squared plus rd theta squared. After a little bit of algebra and the magic of integration, we can add up all of those tiny hypotenuses to get our final formula for the total length L. I mean, how cool is that?
All right, theory is great and all, but let's see this thing in action. We are going to put this formula to the test by calculating the entire perimeter of a very famous curve, the heart-shaped cardioid.
You'll see the process here is pretty much the same every time. We start with our equation, r equals 1 plus cosine theta. Step 1. Find the derivative, r prime, which is just negative sine theta. Easy enough. Step 2, we plug both our r and our r prime into that big arc length formula. And that leaves us with a kind of gnarly-looking integral, which brings us to the most important step of all. Step 3, we've got to simplify it.
Okay, so we're staring at this beast under the square root. What do we do? Well, first let's expand that 1 plus cos theta squared part. That gives us 1 plus 2 cos theta plus cos squared theta. Now look closely. We've got a cos squared theta and a sine squared theta hanging out together. And this is where our old friend, the Pythagorean identity, swoops in to save the day. That pair just becomes a simple 1, and suddenly our expression is looking a whole lot friendlier.
But hold on, we're not quite out of the woods yet. We're left with the square root of 2 plus 2 cos theta. If you've been doing calculus for a bit, you know this feeling. You're so close, but you're stuck. But don't worry, there's another secret key for this lock, the half-angle identity. This awesome trick lets us transform that whole expression into 4 times cos squared of theta over 2. And just like that, we have a perfect square under the square root. The integral is finally ready to be solved.
And so, after all that work, the derivative, the substitution, wrestling with those trig identities, we get a stunningly simple final answer. The total perimeter of the cardioid, defined by r equals 1 plus cosine theta, is exactly 8.
Okay, we totally crushed the cardioid. You're feeling good, right? So let's level up and build on that confidence. We're going to run through a couple more examples just to see how flexible this formula really is.
Let's put two curves side by side. On the left, a spiral, r equals theta squared. The setup is identical, but the integral you get needs a u substitution to solve it, and we end up with a length of 19 over 3. Now on the right, look at this circle, r equals 6 sine theta. This is where the magic happens again. The sine squared and cosine squared terms pop up, add to 1, and leave us with the integral of the square root of 36, which is just the integral of 6.
And the final answer for that circle is 6 pi. Now wait a minute, does that number ring a bell? It should. The equation r equals 6 sine theta actually describes a circle with a diameter of 6, which means its radius is 3. And what's the circumference of a circle with radius 3? It's 2 pi r, which is 6 pi. This is our sanity check. Our big fancy calculus formula gave us the exact same answer as basic geometry. It really works.
Okay, let's take a breath. We've covered a lot of ground. So after all that, what are the most important things you need to walk away with? Let's boil this whole thing down to the essentials.
So what's in your new arc length toolkit? First up, always picture that tiny step along the curve as the hypotenuse of a right triangle. It makes everything make sense. Second, never forget that the Pythagorean theorem is the real powerhouse driving this entire formula. And finally, when you get stuck staring at a messy integral, go on the hunt for those trig identities. They are your secret weapon for making the complicated simple.
So there you have it. We've totally cracked the code on how to measure length in polar coordinates. This is a seriously powerful tool to have in your back pocket. But you know what? It's really just the beginning. It kind of makes you wonder, if we can figure out length, what other secrets like area or slope or even curvature are just waiting to be discovered inside these amazing polar graphs?